Let us now see how we can evaluate the velocity and position vector of a moving particle given the acceleration vector. So we have a moving particle that starts at an initial position that is given by the vector 0, 1, -1, with initial velocity given by the vector I. And its acceleration is given by the vector a of t that is equal to 2 times the vector I plus 6t times the vector j plus 12t to the square times the vector k. We're asked to find the velocity and position vectors at time t. Now, since we know the acceleration vector, we can find the velocity vector by taking the integral of the acceleration vector a of t dt. So that is equal to the integral of 2 times the vector I plus 60 times the vector j plus 12 t to the square times the vector k times dt. So this is equal to the integral of each one of the component functions. So we have integral of 2 dt will give us a 2t times the vector I plus integral of 60 dt will give us 3t to the square times the vector j. And then we have integral of 12t to the square dt will give us a 4t to the third times the vector k. We're also given, so and this is also plus a constant, since we have an indefinite integral, so we have plus a constant c. And we can evaluate this constant c given that the initial velocity vector, so the vector v at t equals to 0 is equal to the vector I. So that is equal to this constant c that we have in our integration. Therefore, that constant c is equal to the vector I. So therefore, the velocity vector at any time t is given by 2 times t times the vector I plus 3 t to the square times the vector j plus 4 t to the third times the vector k plus the vector I. So the vector velocity vector will be equal, if we combine the I, j, k quantities, we'll have 2t plus 1 times the vector I plus 3t to the square times the vector j plus 4t to the third times the vector k. So this gives us the velocity vector at any time t. Now for the position vector, vector r of t, that will be equal to the integral of the velocity vector times dt. So this is equal to the integral of 2t plus 1 times the vector I plus 3t to the square times the vector j plus 4t to the third times the vector k times dt. So that would be equal integral of 2t plus 1 dt will give us t to the square plus t times the vector I. And then we have plus integral of 3t to the square dt will give us a t to the third times the vector j. And then we have plus integral of 4t to the third dt will give us t to the fourth times the vector k. And then plus some constant, let's name that constant d, since we have an indefinite integral. But we are given that the initial position, vector r at t equals to 0, is equal to the vector j minus the vector k. So this is equal to this constant d that we have in the integration that we did. So therefore, the position vector at any time t is given by t to the square plus t times the vector I plus t to the third times the vector j plus t to the fourth times the vector k plus j minus k for d. So if we now combine the I, j, k vectors, so we'll have that the position vector r of t is given by t to the square plus t times the vector I, and then we have plus t to the third plus 1 times the vector j, and then we have plus t to the fourth minus 1 times the vector k. So this gives us the position vector at any time t.